Hello students, good morning. Let us start the class now. In the yesterday's class, we had seen the graphical as well as mathematical definitions of the transconductance. We use the symbol GM for this transconductance, where G in general we can symbolize it as conductance and M we can remember it as mutual. Even though this is not an exact symbol that way, still we can relate it this way. So we had seen the need of finding out GM in case of JFET in contrast with the BJT where we had used beta. So today let us see what is the relationship between VGS and GM, because VGS is the voltage at the input and GM is the relationship between output current and input voltage. Let us see the relation now. The factor 1 minus VGS by Vp is less than unity for any value of VGS other than 0 volts. In fact, this 1 minus VGS by Vp is present in the mathematical expression for GM. It is present in the Shockley's equation as well. So, this particular factor is less than unity for any value of VGS other than 0 volts. Why? You can see here 1 minus VGS by Vp. Naturally, when this VGS by Vp is having some value, 1 minus something, that will be less than unity. So, when this factor will be unity? Only when VGS is 0. When VGS is 0, this right hand side term is going to be 0. So, at that time, the term is going to be, the whole factor 1 minus VGS by Vp is going to be unity. Otherwise, it is less than unity. Now, let us see how it has an implication in our analysis. So, now this means that the magnitude of GM will decrease as VGS approaches Vp, because this factor is less than unity, and yesterday we had seen GM equals GM0 into 1 minus VGS by Vp, and that GM0 value is fixed. So, the magnitude of GM will decrease as VGS approaches Vp. The maximum value of GM occurs when VGS is 0 volts and the minimum value at VGS equals Vp. The more negative the value of VGS, the less the value of GM. That is obvious from this particular expression for GM. Now let us see the plot of VGS versus GM. This is going to be the plot of VGS versus GM. We can see GM0 is here, that is 2 IDSS by Vp, we had seen yesterday. And when VGS equals Vp, you can see here, whenever VGS equals Vp, this is the maximum point there. Maximum point of VGS there. So, here the point where GM0 by 2 corresponds to half of that point in the y-axis, and again Vp by 2 corresponds to this particular point here. Now, when we plot GM versus Vp, we get a straight line like this. Okay, we can take different values of GM and we can keep on plotting the value of GM versus VGS, we get a straight line like this. So, it is told here the maximum value of GM occurs when VGS equals 0, that is this GM0, and the minimum value occurs at VGS equals Vp, this is where VGS equals Vp. Okay, actually when VGS equals Vp, we can see that the value of GM is actually 0. So, that way we can plot a curve like this. So, for the previous example which we had worked out, we can see that here GM is 4 millisiemens when VGS is 0 and GM is 0 when VGS is minus 4 volts. So, that way we can have a plot of VGS and Vp. Now, what is the effect of the drain current on the transconductance? Let us see that. Shockley's equation can be written in the following form. it can be written this way as well. This we had seen earlier. 1 minus VGS by VP equals square root of ID by IDSS. So now substituting into the equation of GM, because this factor which is at the LHS is part of GM. Now we can substitute this where we can write GM equals GM0 into 1 minus VGS by VP, or GM0 into square root of ID by IDSS. Now we know that this GM0 is a fixed value, IDSS is a fixed value, only ID is going to vary, which means GM is proportional to square root of ID, which is obvious from this expression. Again, GM0 is a fixed quantity, IDSS is a fixed quantity. So these two factors are not going to affect GM as such. But that ID will be varying, accordingly GM will be varying. So we can say that GM is proportional to square root of ID. Now that is the relationship between GM and ID. GM can be determined for a specific value of ID, a few specific values of ID. That means if we know ID, we will be knowing GM0, we will be knowing IDSS, we can compute GM and we can have a plot of ID versus GM. If ID equals IDSS, then GM is GM0 itself, because square root of IDSS by IDSS is 1. If ID equals IDSS by 2, then GM equals GM0 into square root of 2. So it is 0.707 into GM0, square root of 1 over 2. It is 0.707 into GM0. If ID equals IDSS by 4, GM equals GM0 into square root of 1 over 4, that is GM0 by 2, that is 0.5 GM0. So we can see that when ID equals IDSS, GM is maximum. And when ID is IDSS by 4, GM is 0.5 GM0. Now you can recall how we applied the Shockley's equation and how we had 0.5 VP corresponding to IDSS by 4. When VGS was 0.5 VP, it was corresponding to IDSS by 4. Here also we can see that when ID is IDSS by 4, GM is 0.5 GM0. What does it mean? We had already plotted the curve of GM0 versus VGS and we had got a straight line there. We had got a straight line, which means that here also when ID is IDSS by 4, that is corresponding to VGS itself, right? Because GM and VGS are directly proportional. That is how we got a straight line there. So it is obvious that when ID equals IDSS by 4, we get GM equals 0.5 GM0, just like we had got there 0.5 VGS, or VGS equals 0.5 VP. Let us plot ID versus GM now. When we plot ID versus GM now, you can see this. We had the maximum value 4 millisiemens in the earlier example. Now you can see when ID is IDSS by 4, let us say IDSS was 8 milliampere, taking that example, IDSS by 4 corresponds to 2 millisiemens, that is 0.5 GM0. And IDSS by 2 corresponds to 0.707 GM0, that is 2.83 millisiemens. And when it is IDSS, we get GM0, that is 4 millisiemens. Now when we join these 3 points along with the origin, why origin is coming into picture here? You can look at this expression, previous expression. When ID is 0, naturally GM is 0. Square root of ID, when ID is 0, naturally GM is 0. So here, when ID is 0, GM is 0. So origin is also one of the points. Now we join all those 4 points, we get a curve like this. You can see that the plot of ID versus GM is non-linear, whereas the plot of VGS versus GM is linear. Okay. Why it is non-linear? Basically, we have seen that the transfer curve is also non-linear. We had seen earlier that ID versus VGS was also non-linear. Now naturally, GM versus ID also has to be non-linear. And we had seen that GM versus VGS is linear. Now we have to come to a conclusion. let me start from x-axis. VGS versus ID is nonlinear, whereas VGS versus GM is linear. So naturally, ID versus GM has to be nonlinear, because GM and VGS are directly related by means of a linear equation. So when VGS versus ID is nonlinear, naturally ID versus GM also has to be nonlinear. That is the conclusion. Anyhow, only when this characteristic is nonlinear, that is when we can have a device that is nonlinear, right? All the active devices are basically nonlinear. Only the passive devices are linear. That we already know. So naturally, we should expect a nonlinear curve only as far as the output is concerned. The highest values of GM are obtained when VGS approaches 0 volts and ID approaches IDSS. That we have already seen here. When VGS approaches 0 volts, we have maximum value of GM, and when ID approaches IDSS, then also we will have maximum value of GM. These two things we have seen. Now let us discuss the input impedance and output impedance of the JFET. And these factors we had extensively discussed in case of BJT. Let us recall the basic requirements in case of any amplifier circuit. Ideally, we want infinite input impedance. Ideally, we want zero output impedance. Ideally, we want infinite voltage gain. Ideally, we want infinite bandwidth. And our list goes on. We want many ideal things to happen from our circuits. But ideally, any one circuit will not give us all these characteristics. So what we do is, we combine all such circuits in cascade or in series, such that we will have a multi-stage amplifier where we will somehow obtain our desired characteristics. So let us see what is the case of input impedance with the JFET. Now we can immediately come to a conclusion that JFET will have a larger input impedance when compared to BJT. Can anybody tell me why? I am telling you that we can immediately come to a conclusion that JFET will have a larger input impedance when compared to BJT. Can anybody tell me why? Either you unmute and tell me, or you put the answer in the chat box. Because it is already on stage. No, that is not the exact answer. Both will be on. Even BJT will be in the middle of the load line, and even JFET will be in the middle of the transition curve or transfer curve. We are keeping both of these switches in the half on, half off state. That is not the exact answer. Any other answer? The exact answer is, there is no gate current in case of JFET. In BJT we had a base current. Because of the base current we had beta there. And we had that beta into RE at the input side. Now in JFET there is no beta at all, when there is no input current at all. Naturally, when the input signal is coming there, it is going to see a wall there. Wall in the sense, between the gate and the channel there is a reverse biased PN junction now. When the reverse biased PN junction is there, you already know that the reverse biased diode will have a very high resistance. When the diode is in the reverse biased condition, the current which is flowing through the diode is only because of the minority carriers. Whereas in case of BJT, it was a forward biased PN junction, right? Between the base and the emitter, it was a forward biased PN junction. And that is where we had the dynamic resistance of the emitter, which was modeled. And at the base, we had multiplied it by beta, and we had a factor called beta into Re there. But in JFET, as we have a reverse biased PN junction, and as the current which is flowing is only due to the minority carriers, the input impedance of the JFET is going to be much larger than the BJT. Now that is the very first advantage of using JFETs as well as MOSFETs, which are field effect devices. Now you can see the input impedance of JFETs is sufficiently large, typically above 1 giga ohms. Now think about this. We had few kilo ohms of resistance as input impedance when we worked with the BJT circuits. Now here you can see typically the JFET's input impedance itself is above 1 giga ohms. And for all practical purposes, it can be assumed that the input terminals approximate an open circuit. When there is an input impedance of 1 giga ohms, now how much of current can flow? The current will be in nanoampere. Even if the input voltage is in volts, you can see giga is 10 power 9. So naturally, 1 over 10 power 9 is 10 power minus 9. Current will be in nanoamperes. Whereas in BJT, we had current in microamperes and milliamperes at the input side. Okay, at the input side, it could be microamperes also in case of BJT. Here, it is 1000 times more than BJT. So for all practical purposes, the input terminals can be approximated as open circuit. So in the equation form, we can write it as Zi of JFET equals almost infinity. What about the output impedance now? Just like I asked you a question about input impedance, can any of you tell me what may be the output impedance of JFET when compared with BJT? Just visualize the BJT circuit. With the BJT, we had that R0 there, which used to be given or provided by the manufacturer himself. And you can always visualize BJT when it is operating in the quiescent conditions. The output junction is reverse biased and the input junction is forward biased. Here also in JFET, the output junction is reverse biased, but even the input junction is reverse biased. But we have already covered the input side now. What about the output side? Will the output impedance of JFET be larger than BJT or lesser than BJT? Any answers? Lesser than BJT. Fine. How? If it is less than BJT, how or why? Okay, let me tell you the answer. In BJT, we had a collector to base, then base to emitter. We had 3 regions there, 2 junctions there. Whereas in JFET, between drain and source, it is a continuous channel. It is a N-type channel for a N-type JFET. So, there is no junction in between drain and source. Whereas there used to be junction in between collector and emitter. So that is how the output impedance of JFET will be lesser. Let us see. The output admittance is indicated as GOS or YOS. We can call it as impedance also, we can call it as admittance also. 1 over Z is admittance itself. By the way, I recall my yesterday's question. Can anybody give me the answer for the other 3 things? Actually, for 3 things already we have answer. For the other 2 things, 1 over resistance is conductance, 1 over capacitance is elastance. Yesterday, I think Lokesh Biswas had given that answer. And 1 over impedance is admittance. That also you know. What about 1 over inductance? And what about 1 over reactance? Anybody has answer? Okay. Today, Rohit has given the answer. 1 hour reactance is susceptance. Okay, that is correct. What about 1 hour inductance? Anybody has the answer? Fine. 1 hour inductance is reluctance. Okay. These are all interesting terms. Now I'll tell all these 5. Resistance, capacitance, inductance, reactance, impedance. Now I'll tell you the reciprocal of all these 5. Conductance, elastance, reluctance, susceptance, admittance. Now you can think about the English meaning or etymological meaning of these words. Resisting and conducting, capacity and elasticity, inducing and reluctant, reacting and then susceptible, impeding then admitting. You can find out the exact meanings of these 10 words in English language. Then you can relate them that way. These are quite interesting terminologies. When the physical scientists had to name all these properties, they must have thought a lot about how to call them using an English word. So we should again and again appreciate all those people, all those scientists who had worked earlier with all these materials. Okay, let me come back. The output admittance is indicated as GOS. Instead of impedance, we can always call it as admittance, which is simply 1 over Z. We can give it as GOS, where O stands for output, or YOS, with the unit of microsiemens. The typical values range between 10 microsiemens to 50 microsiemens. The subscript O signifies output network parameter and S signifies the terminal source in the model. Therefore, output impedance in the equation form is Z0 JFET equals RD equals 1 over GOS equals 1 over YOS. It is 1 over GOS. Now you can see 10 microsiemens, 1 over 10 microsiemens, 50 microsiemens, 1 over 50 microsiemens. Is it lesser or larger? Now the thing is, admittance is lesser, impedance will be larger. In fact, in the case of JFET, as it is a reverse biased junction, I had told you in the case of BJT also that the collector junction is reverse biased. Even in the case of JFET, even though drain and source in between them, if there is no other junction, basically that junction is a reverse biased junction, right? N is connected to positive of the battery. So naturally, admittance will be lesser, impedance will be larger. Actually, when impedance is larger, we have some advantage. When impedance is lesser, we have some advantage. If at all we are cascading two circuits, if the output impedance is larger, it is better for us. How? When we cascade two circuits, if the output impedance of the previous circuit is larger, it will correspond to the larger input impedance of the next stage. That way we have impedance matching there. And I had told you earlier that you will be studying a theorem called maximum power transfer theorem in the course called network analysis, where you will understand that when two impedances are equal, only then highest power will get transferred. When the source impedance and the load impedance are equal, then the highest power gets transferred. So naturally, whenever we cascade the circuits or when we connect two amplifiers in series, when the next stage of the next input impedance of the next stage is going to be larger, naturally we want the output impedance of the previous stage also to be larger. That way JFET is helping us. But now you may ask me, sir, you only told me that output impedance has to be ideally 0. Yes, correct. Output impedance has to be ideally 0 only when we connect the actual load. For example, in the case of a multi-stage amplifier, at the last stage we will have an amplifier. In the last stage, we are going to connect the loudspeaker as the load for an audio amplifier. Now, in that case, the loudspeaker has to draw a lot of power from the power supply so that to produce sometimes some kilowatts of output. Normally, few watts of output, sometimes kilowatts of output. Now, when you are listening to my speech in your earphone now, the output of the earphone will be few milliwatts because you are directly connecting the earphone to your ears. There no much of power is required. But if you are connecting this to your laptop or desktop and listening to the class directly in the open mode, at that time the laptop or the desktop will be having a few watts of power at the speaker because now the gain is more there. If at all you connect this to a stereo system and if you listen, the stereo system can produce kilowatts of power because when you play the stereo music or stereo sound, it is audible to the neighboring houses also. Now it depends on the application there. So at the last stage when we have an amplifier, the very last stage is supposed to be a power amplifier based on the application. Now when we connect a very low impedance speaker, it is going to consume a very large power. So naturally there the output impedance of the amplifier must be ideally 0 or it must be very less. For example, if you are connecting a 4 ohm speaker as the load, now output impedance of the amplifier is supposed to be 4 ohms because that 4 ohms and 4 ohms will match with each other and that is when maximum power will get transferred. Now, if at all you have a 12 volts supply to that last stage of amplifier, you can imagine that the current which is drawn by this speaker is 12 divided by 4, that is around 3 amperes. 3 amperes is really a very large current. Now you can calculate the power, that is 12 volts into 3 amperes. Voltage is 12 volts into 3 amperes. So around 36 watts of power is going to be consumed at the output stage. But here we are not discussing about the power amplifier. We will discuss the power amplifier in the last module in our course. Otherwise, we are discussing only the pre-amplifier stages. That means the amplifier stages which are at the input side, not at the output side. That is why here JFET is better than BJT in the sense JFET's output impedance is now larger than BJT. This is in contrast to whatever I told a few minutes before. I wanted you to think about this particular concept such that you will recall whatever I had told in the previous module about the output impedance. In fact, whatever I had told in the last few minutes, I had already discussed this fact when we discussed the BJT circuits. So, naturally Z0 or JFET is indicated as RD, drain resistance. There we had RE, emitter resistance, or R0, output resistance. Here also we can call it as output resistance R0, or we can also call it as RD, drain resistance. That is 1 over GOS is also equal to 1 over YOS. On the characteristic curves, the output impedance is the slope of the curve at the point of operation. The more horizontal the curve, the greater is Z0. Let us see that later on. Now, in the equation form, RD is delta VDS by delta ID because at the output side we have VDS and ID. X-axis will be VDS, Y-axis will be ID, and you are already familiar with that particular curve. You have to visualize the cutoff region, the ohmic region, and the saturation region. The saturation region is the region where the JFET is operating in the quiescent conditions, whereas the ohmic region corresponds to completely on condition and cutoff region corresponds to completely off condition. Now we are going to measure this drain resistance basically in the saturation region or during the quiescent conditions. So that is delta VDS by delta ID. If you recall the output characteristics, you will remember that in the ohmic region, it is like a straight line. There it is also called as linear region. and in the saturation region or in the quiescent conditions, when it is half on and half off, the curve is almost horizontal to the x-axis. It is like a straight line that is horizontal to the x-axis. Now what does it mean? It means that delta ID is very less there and delta VDS is very large there. So when delta ID is very less there, this RD is going to be much larger for a given value of VGS. So we should say that the output impedance of JFET is much larger than BJT. Because in BJT, that particular curve was not exactly horizontal to the x-axis. It was slightly progressing upwards only. There used to be a finite slope there. Whereas in JFET, this line is almost horizontal to the x-axis. So naturally, slope will be much larger. You can see this. Whatever I had told till now, it is the same thing here now. You can see this. This delta ID is much lesser here and delta VDS is much larger here. Because the delta ID is much lesser here, here the numerator is much lesser. When the numerator is much lesser, naturally RD will be much larger. Even though delta VDS is larger. Remember, this VDS is in volts, whereas ID is in milliamperes. So naturally, at the numerator, you will have a small factor into 10 power minus 3. So, when that into 10 power minus 3, when it goes to the numerator, it becomes into 10 power plus 3 multiplied into this delta VDS. So, naturally, RD is going to be much larger for a given VGS. Now, this can be measured for all the three curves. The value of RD is different for each value of VGS and hence RD changes from one operating region to the other. There will be a slight change of RD for the given value of VGS. This is slightly different from what we had seen in case of BJT. In case of BJT, in general, the manufacturer is going to give us the output resistance R0 and we are going to substitute that value in our analysis. But here the value of RD can slightly change for a given value of VGS. So from one operating point to the other, the RD will change. Largest value of RD occurs for the least value of VGS and hence the smallest value of RD occurs when VGS equals 0. You can compare these three curves, whereas the lower curve or lowest curve is very much nearer to x-axis, whereas the upper curve or uppermost curve is away from the x-axis. So you can always observe that the slope here is also different. Now when the lowermost curve, when it is very nearer to x-axis, the slope will be much larger there. And when the uppermost curve is slightly away and there is slight difference when compared to the parallel nature to the x-axis, we can always see this difference here. So largest value of RD occurs for the least value of VGS and hence the smallest value of RD occurs when VGS equals 0 volts. You can see here when VGS equals 0 volts, the RD will be smallest and RD will be largest for the least value of VGS. Let me admit the student who is waiting. Let me go to the next slide now. Based on the discussion of all these points, let us try to draw the AC equivalent circuit for JFET now. We had written the AC equivalent circuit for BJT by using a model called RE model. Please remember that at the input side we had beta RE and at the output side we had a current source with IC and we had a parallel resistance indicated as R0. Please remember that we had used that particular model for our AC analysis. Now similarly for the JFET, let us have an equivalent circuit. You can see this equivalent circuit. At the input side, there is no resistance at all. Why? because at the input side it is a reverse biased PN junction. So at the input side we are considering the input impedance to be infinity, even though practically it is 1 giga ohms. That 1 giga ohms also we need not write here. Why? Because even if you write 1 giga ohms, the current flowing there will be only nanoamperes. So we can as well ignore them, because at the output side the current will be in milliamperes. So we can, if as there is a 10 power 6 difference, we can ignore the resistance at the input side. So it is written as an open circuit here. Between gate and source, we can as well consider it as open circuit. But at the output side, we can write this GM into VGS. At the input side, we have a voltage. That voltage is VGS. But there is no resistance. At the output side, we have a current source. From the drain to source, there is current flowing. And that we can indicate as GM into VGS. Why? GM is nothing but the transconductance. There in the BJT, we had indicated this as IC, and we had always calculated IC as beta into IB. Here, instead of that beta, we are using GM, and GM into VGS is the current that is flowing at the output side. And as I had already discussed in the previous slide, we have this drain resistance or output resistance, which we can write in parallel to the current source, and we can indicate it as RD. Now this is going to be the JFET's AC equivalent circuit. Now using this AC equivalent circuit, we can analyze the biasing circuits which we had discussed earlier. We had already performed the DC analysis for fixed bias, self bias and voltage divider bias. Now as far as AC analysis is concerned, in BJT also we did not consider self bias. Why? Because that emitter resistor had a parallel capacitor which was called as bypass capacitor. So the AC analysis self bias was same as that of fixed bias. It is the same case with JFET as well. So here in the AC analysis we need not discuss about self bias. Now we will focus on fixed bias and voltage divider bias. The input impedance is represented by the open circuit at the input terminals, and the output impedance is represented by the resistor RD from drain to source. At the output, the control of ID by VGS is included as current source GM into VGS connected from drain to source. This point I had already explained a few minutes before. The current source has its arrow pointing from drain to source to indicate a 180-degree phase shift between output and input signals in the common source configuration. This is same as our convention which we used in BJT circuits, and you are already familiar with it. And here we are discussing only common source configuration. We are not going to discuss common drain configuration as such, because we had already done it with BJT. The same things hold good in case of JFET as well. And this fact also I had told you yesterday. Just like in a common collector configuration, we also called it as emitter follower, and there the voltage gain is unity. In the same way, in case of JFET also, common drain configuration is called as source follower, and here also the gain is going to be unity. So we are not going to deal with that particular circuit. Okay. Now let us see the fixed bias configuration in case of JFET. Any questions till now? If you have any questions, you can ask me, or else I will proceed. Okay, no questions. Let me proceed. Let us start with the AC analysis of the first configuration, that is fixed bias. Now this is the circuit which we had used. We had used the power supply at the gate. We had two power supplies. One was this negative gate voltage at the gate in order to have a reverse bias at the input side, and we had used this RG to prevent the AC signal being absorbed by the power supply. Now, we can write the AC equivalent circuit for this. We can replace this capacitor with the short circuit, and we can replace this C2 also with a short circuit. And VDD is our AC ground, even VGG is our AC ground. VGG is also AC ground. All power supplies are basically AC ground, and capacitor is short, and we can replace the JFET with its AC model. So what we get is, at the input we get only this RG connected to ground, because at the input this VGS is there, but the gate to source there is no current, it is an open circuit. So at the input side we will see only this RG connected to ground, and at the output side we will have that current source GM into VGS along with the small RD and the capital RD connected to ground. You can easily visualize the AC equivalent circuit. Anyhow, I am going to show you the circuit now. C1 and C2 isolate the DC biasing arrangement from the applied signal and the load, and they act as short circuit equivalents for the AC analysis. This we already know. When the values of GM and RD are determined from either the DC biasing arrangement or the specification sheet or the characteristic curves. See, we have three choices now. If the manufacturer gives the specification sheet, we can get GM and RD from them. Or else, from the DC biasing arrangement itself, we can deduce GM and RD by using DC analysis. Or else, we can also get it from the characteristic curves by measuring the slope. So we have three methods now. We had already seen the mathematical definition of GM and the mathematical definition of RD. So it is possible to obtain the values of these two things on our own also. So the AC equivalent model of the circuit can be substituted between the appropriate terminals. Now let us see the AC equivalent circuit. This is the AC equivalent circuit now. Battery is replaced by a short circuit because it is AC ground, and we have RG, capacitor is shorted, and here also capacitor is shorted. Now the capital RD is connected to ground because that is also battery replaced by short. Then we have the regular AC model of the JFET, which is highlighted in the blue color here. Between gate to source it is open circuit here, and then we have a current source, then we have the small RD, which is the drain resistance. Now using this we can solve the exercises for the fixed bias circuit now. Now the same circuit can be written in this fashion directly without using the ground symbols. From the input we have Zi, Zi is this RG, and we have this open circuit between gate and source. There is no current there. Then we have the current source here, GM into VGS. Then we have the small RD, then capital RD. So what is the Zi now? Zi is nothing but RG, which means in BJT we had that RB parallel with beta into RE. Always beta into RE used to be lesser than RB. Now you see here, there is no beta into RE factor at all here at the input. That means the value of resistance which we connect, that itself is deciding the input impedance. And we can connect a very large resistance also at the gate. Why? Because the purpose there is reverse biasing, right? It is not forward biasing. So no need of gate current there at all, right? So even we can connect a 1 gigaohm resistance, 10 gigaohm resistance. It does not matter much now. So the input impedance is completely decided by the gate resistance that we connect. That's all. And that resistance, its purpose is only to isolate the input signal from the gate power supply. Otherwise, there is no other requirement there. So we can connect a very high resistance at the gate. Now similarly, the output impedance is small RD in parallel with the capital RD. You can see this here, small RD parallel with capital RD. And we have already seen that the small RD is much larger in case of JFET when compared to BJT. Now this capital RD is the value which you choose based on our Q point. Actually, this capital RD decides the drain current as well. So here we don't have much freedom now. So Z0 is small RD in parallel with capital RD. So Zi is RG. Z0 is capital RD in parallel with small RD. Now the last one left is we have to find out the expression for the voltage gain. And we already know that in BJT we had always compared output versus input, and that is how we had derived the expression for voltage gain. Let us follow the same procedure here. Z0 we can approximate it to capital RD, because in general the small rd is greater than or equal to 10 times that of capital RD. This is a general conclusion, but my suggestion would be that you always remember this upper equation only. You always remember Z0 equals capital RD in parallel with small rd. Let us not ignore small rd also when it is given in the exercise. Now we have this V0 equals minus Gm into Vgs into Rd parallel with Rd, right? We have to get an equation for output voltage. Output voltage is current into resistance. Resistance is known, output impedance, and current is known, Gm into Vgs. And Vi is nothing but input voltage between gate to source, that is Vgs. So V0 is minus Gm into Vi into Rd parallel with Rt, because this Vgs term is there. So we can simply find out V0 by Vi is minus Gm into Rd parallel with Rd, or voltage gain AV is V0 by Vi equals minus Gm into Rd parallel with Rd. Or we can say AV is V0 by Vi into minus Gm into capital Rd when we ignore the small rd. But my advice would be, let us not use the lowermost equation, let us always use the upper equation, that is AV equals V0 by Vi equals minus Gm into small rd in parallel with capital Rd. Remember these three equations. In the next class, let us solve some exercises on fixed bias as well as voltage divider bias.